Okay, so I'm going to be talking about a project that we've recently uploaded to archive, and it's the title is an empirical survey of the effectiveness of debiasing techniques for pre-trained language models. And this was work that I did with a really good undergrad student at McGill and my supervisor, Siva. So this problem probably needs a little motivation. So we've all seen that these large pre-trained language models have performed really well across a range of tasks in NLP. But there's also been a lot of work that's shown that these models learn social biases from the large amounts of text that they're trained on. So for instance, there's been work that's shown that contextual embeddings from pre-trained language models like BERT can tend to contain gender bias. So for instance, representations for female words may be more closely associated with concepts of parenting, whereas representations for male words may be more closely associated with, say, science or mathematics. There's also been work that's shown that GPT-2 can be easily prompted to generate toxic text. And finally, there's also been some recent benchmark data sets for measuring bias, which I'll talk about shortly, like Stereoset, which demonstrate that models contain stereotypical biases. So because of these findings, there's been a lot of work that's focused on developing techniques to mitigate these social biases in language models. And this is a really practically important problem because we want to be able to deploy these models in real world settings. So the proposed techniques are often not investigated very thoroughly. So typically the techniques are only investigated in the context of mitigating gender bias, but obviously we're interested in mitigating other types of social biases. And there's also not a significant investigation of how debiasing impacts language modeling and downstream task performance. And these are both things we want to make sure that these debiasing techniques have minimal impact on. So in this survey paper that we conducted, we performed an empirical survey of the effectiveness of 5 debiasing techniques for 4 pre-trained language models. And our hope in carrying out this survey was that we could, first, I wanted to get a better overview of how these techniques or how effective the current state of these techniques are. But also we wanted to better direct future research in bias mitigation. So for today, I'm going to be talking about 3 research questions that we addressed in our paper. So the first was just, of our 5 debiasing techniques that we studied, which is most effective in mitigating bias? And then we were also interested in seeing if these techniques work beyond the gender bias domain. So if we adapt these techniques to mitigate, say, racial bias, are they still effective? And finally, how significant of the impact do these debiasing techniques have on a model's language modeling ability? So for the remainder of the talk, I'm going to begin by first giving an overview of 3 debiasing techniques that we studied, so a subset of the 3 of the 5. Following this, I'm going to introduce a benchmark that we used for measuring bias in language models. And then finally, I'll present a small subset of results for BERT on this benchmark. And then I'll conclude with some high-level takeaways and some limitations of our work. So the first debiasing technique that I'll introduce for these language models is counterfactual data augmentation. So this is a database debiasing strategy that is typically used in the context of mitigating gender bias. And it involves augmenting or essentially rebalancing a corpus by swapping terms. So it's kind of the most simple heuristic that you could come up with. So you can imagine having sentences like the woman was a nurse and swapping woman with man. The man was a carpenter swapping man with woman, or the Jewish man was greedy and swapping Jewish with Catholic. And then the idea is that you can debias a model by making use of this rebalanced corpus somehow. So the typical setup is that you would then further train your model on this augmented data set. So the second debiasing technique that I'll discuss is sentence debias. So this is a debiasing technique that's more so focused on debiasing the representations within a model itself. So this is a post hoc projection-based debiasing technique. And the rough idea is that you want to be able to estimate some directions in your model's embedding space that are associated with some bias. So for instance, in this is a really simplified figure, but you can imagine having all of these words or encoding all of these words with your model and obtaining some contextual embedding. And maybe there's some indirection in that embedding space that roughly corresponds to gender. So on the left here, in one direction of this dimension, you might have words that are stereotypically associated with men, and on the other side, stereotypically associated with female. And the idea is to debias the representations within the model by kind of zeroing out this direction from the representations. So you're effectively removing all of the gender information from these representations. So the final debiasing technique that I'll describe is this recent self-debiasing technique. So this is a debiasing technique that requires no additional training or data. So it's very promising in that sense. And the rough idea is that you leverage the model's internal knowledge to debias text generation. So roughly the idea is that you can first prompt the model to generate text containing some attribute you want to mitigate. So for instance, you could prompt GPT-2 to generate sexist text. And then you can perform a second normal generation process where you rescale the probabilities of tokens that are high under the previous toxic generation. So for instance, when you're generating this sexist text, there might be certain tokens that are very probable under this prompt that you provide to the model. And then you can downweight those tokens during your normal generation to reduce the risk of generating text of a particular or exhibiting a particular attribute. So I've introduced the 3 debiasing techniques that I'll provide results for, but now I'm going to talk about the benchmark that we're going to use. So we make use of a Stereoset as one of our benchmarks in our paper, and it's a crowdsourced benchmark for measuring bias in language models across 4 domains, so gender, race, religion, and profession. And the rough idea of this data set is that you have a collection of examples, and each example consists of some context sentence with some word masked. And the idea is that you want to score how often the model assigns a high probability or the highest probability to each of the 3 candidate sentences or candidate tokens. So one candidate is stereotypical, the other reflects an anti-stereotype, and the third is just an unrelated association. So from this collection of examples, you can obtain 2 scores from Stereoset. So the first is just what I previously described, which is the stereotype score. So this is the percentage of examples for which the model prefers the stereotypical candidate over the anti-stereotypical candidate. But then you also, Stereoset also provides a very crude measure of the language modeling ability of a model. So you can also score how often the model prefers a meaningful association. So this would be either a stereotype or an anti-stereotype over the unrelated association. And that provides you a very coarse measure of a model's language modeling ability. So I'm going to, so here's a small subset of results. So we evaluated each of our debiasing techniques against Stereoset, and we considered gender, racial, and religious biases. So on the far left here, this green bar is just the baseline BERT model, which has a stereotype score of 60.28%, which means that it prefers a stereotypical completion for a sentence roughly 60% of the time. And each of these other bars is BERT with the corresponding debiasing technique applied. So we see in the gender domain, all of the techniques are effective in reducing the stereotype score, which is promising. And for race and religion, we also observe similar trends. The only abnormality here is that for BERT and race, sentence debias actually increases the stereotype score of the model. So this is really promising that these debiasing techniques seem to be working well beyond the gender domain. So in addition to evaluating or measuring bias in language models, we're also concerned with seeing the impact that these debiasing techniques have on a model's language modeling ability. So we can look at the language modeling scores that we can obtain from Stereoset. And here, a higher language modeling score is indicative of better language modeling ability. So we can actually see that all of these techniques have very negligible impact on a model's language modeling, which is also really promising. And in fact, we actually see that CDA, or counterfactual data augmentation, actually increases BERT's language modeling language modeling ability. And we observe similar trends for race and religion. So I'll finally conclude with a few limitations of our work. So first, since we are only evaluating existing techniques for mitigating gender bias, our work makes use of a binary definition of gender, and we leave extensions beyond this binary setup to future work. Since Stereoset, the benchmark that I provided results for, was collected using North American crowd workers, it may only reflect North American biases. And finally, our experiments only considered English language models. So I've only presented like a small subset of the results from the paper, but if you're interested in this direction, I would encourage you to check out our paper. And that is everything.